Hey guys, so in today's video we are going to be taking a look at a concept called net ionic equations. And net ionic equations can only be written for double replacement reactions. So that is what we are going to be looking at today. So let's take a look at the double replacement reaction below. Here we are looking at a reaction between potassium chromate and lead 2 nitrate. And the first thing you have to do when you're trying to determine a net ionic equation is you have to actually predict the products and the phases of matter for those products. So I've already gone through and I've predicted the products for you, but now you need to use your solubility rules to figure out the states of matter. So using your solubility rules, you should find that the lead 2 chromate product that we're going to have at the end here is going to be a solid, and that our potassium nitrate is going to be aqueous. And so this is the type of chemical reaction that we've been writing in the past couple of classes. This equation is the one that's going to show the phases of matter for all of the species, and what species is really talking about is chemicals here, and it keeps all of the compounds together. So we see our compounds in a way that we're used to writing them. And we call this a molecular equation. But we know that aqueous means dissolved in water. So we know that any of the aqueous substances are going to be able to break down into the ions that make them up. So what we're going to go ahead and do right now is we're going to look at the equation above. We're going to be looking at this equation we were just working with, and we're going to break all of the aqueous substances into the ions that make them up, and all of the solids are going to remain the same. So I'm going to start with my potassium chromate. So in my potassium chromate, I see that I have 2 potassium ions, and each potassium ion has a +1 charge. And then it keeps the state of matter aqueous because it's this ion dissolved in water. And we're going to add that with our 1 chromate ion, CrO4 2-, which is also aqueous, plus our lead 2 nitrate. So we're going to do the lead 2 part, plus our 2 nitrate ions that we see. And then we're at our arrow, so we're going to draw our arrow. Remember, the solids are going to stay together, so that lead 2 chromate is going to stay as lead 2 chromate. But we can break apart the other product into 2 potassium ions and 2 nitrate ions. So when we break the chemical reactions up into the ions, this is what we call a total ionic equation. And again, what we've done here is we've taken a look at the chemical equation that was at the top of the screen, and we've broken it down into all of the ions that would dissolve in the water. And remember, the solid stays intact because that solid is insoluble. It's not going to be able to dissolve in the water. So let's take a look at what we're going to do next. So all I've done here is recopy the equation from the first page onto the second page, our total ionic equation. And what do we notice about the total ionic equation? Well, hopefully something you saw is that we see the same ions appearing on both sides. So here we see our potassium ions as the reactants and our potassium ions as the products. We see our nitrate ions as a reactant, our nitrate ions as a product. And so ions that are going to appear in the same form, that's kind of a key word here, the same form on both sides of the equation are what we call spectator ions. And I want you to think about what that word spectator is. Hopefully you've all been to a concert or a sporting event. And what are the spectators? Well, the spectators are the people who are in the stands. They're the ones who are watching what's going on, but they're not actually doing anything to influence the outcome of the sporting event or influence the performance at a concert. And so spectator ions in a chemical equation are things that aren't going to change. And so because they don't change, they don't actually participate in the chemical equation. So now what we're going to do is we're going to take those spectator ions out. So again, when we look at the equation above, potassium is going to be a spectator ion, nitrate is going to be a spectator ion, and those are the only 2 ions that we see in the same form on both sides of the equation. So now if we go and rewrite our equation without those spectator ions, we're going to end up with the chromate ion plus the lead ion to produce the lead to chromate product. And when we have this, when we take out only, we take out all the spectator ions and we're leaving only the ions that form the solid product, we call this our net ionic equation. It boils it down to what is actually happening in the chemical reaction. All right, so we're going to do this one in pieces together, and you're going to have some questions embedded in throughout. So the first thing we have to do when we're looking at a net ionic equation is we need to write the molecular equation. So let's start with that. So silver nitrate. We know silver is Ag, nitrate is NO3. Remember, silver has a charge of +1 and nitrate has a charge of -1. So I have no extra subscripts in this reaction. And the silver nitrate is going to be aqueous. And we are reacting it with iron. And this 2 here tells us that we've got iron 2+. And chloride is chlorine with a -1 charge. So we have FeCl2. And I know that these states of matter are aqueous because it tells me that this reaction is happening in water. And since they're ionic compounds, they're going to be aqueous. So now I need to think about the products that would form. So remember, in a double replacement reaction, the cations and anions are going to switch what they're bonded to. So the iron is going to bond to the nitrate, and the silver is going to bond to the chlorine. And remember, cations always get written first. So my products are going to be silver chloride now and iron 2 nitrate. And then I have to go to my solubility rules, and I have to figure out what the states of matter of each one is. So the silver chloride is going to be solid, and the iron 2 nitrate is going to be aqueous. So this is my molecular equation. I'm going to rewrite that. It's kind of sloppy, and I don't want it to be sloppy in your notes. So now that we have our molecular equation, we need to write the total ionic equation. So the first question I'm going to ask you is, what kind of compounds can we split into ions, and which kind of compounds have to stay as they are in the equation? Hopefully you wrote down that the ions that are going to split into, or the compounds that will split into their ions, are anything that's aqueous, and the things that are solid are going to stay as they are. So now let's write our total ionic equation. So we're going to, oh, you know what? I'm sorry. We have to do one other thing first. We need to balance this equation. So go ahead and let's balance it together. So silver is balanced, nitrate is not, so I'm going to put a 2 in front of the silver chloride, I'm sorry, the silver nitrate. And because I put a 2 in front of the silver nitrate, I also need to put a 2 in front of the silver chloride. And I believe that that balances the reaction now because iron is 1 on both sides. Okay, so now that we've done that, let's go ahead and do our next step where we're going to write the total ionic equation. So I have 2 silver ions plus 2 nitrate ions plus an iron 2 chloride ion plus 2 chlorine ions to produce my silver chloride, which is my solid, so it has to stay together, plus another iron 2 chloride ion plus 2 nitrate ions. Now that I have my total ionic equation, I'm going to be looking for the ions that appear in the same form on both sides of the equation. What do we call those ions? Hopefully you remember that we call those ions our spectator ions. So let's take a look. What would be some of our spectator ions in this equation? Hopefully that you picked that the spectator ions are going to be the nitrate, because we see 2 nitrate ions on both sides, and the iron, because we see iron on both sides in the same form. So remember, this is what we call our total ionic equation. And now we need to take it one step further, and we're going to write our net ionic equation. Remember, in the net ionic equation, we simply take out the spectator ion. So we're going to write everything else that's been left. So we're going to write our 2Ag plus 2Cl to produce 2 silver chloride. And remember, this is what we call our net ionic equation. Just to recap, when you're writing your net ionic equation, you always need to start with your molecular equation first, and you write it out, you balance it, and after you've balanced it, you're going to write your total ionic equation, where you split all of the aqueous compounds into the ions that make them up, and all of the solids stay as they are because they're insoluble. After that, you determine what the spectator ions are by looking for the ions that appear on both sides of the equation in the same form. And once we remove the spectator ions, then we can write what we call the net ionic equation. Good job, guys.